want to pass these out in the beginning right before we start. They're just evaluations. I need them filled out before the session. And the session number for the top is 05. Those out. Yeah. All right. So before I start, I just want to give you guys a heads up that this is being live streamed and recorded, just as a heads up. All right, so for today, I just got a few questions together from chapters 7, 8, 9, and 10. And we're just gonna go through those problems. And at the end of the session, just if you have any general questions, then all screws and everything. Problem is internal normal force, shear force, and moment at point D in the beam. So then from here, our first thing that we want to do is find our support reactions. We have a pin support at A, so that has the two forces, the horizontal and vertical forces. That AY. Okay. So then two support reactions at A, the force FBC coming in at an angle, the applied force, and then the distributed loading, which I concentrate to five. So from there, we can take moments about point A, and then in taking, I believe that's clockwise to be positive, should equal, all the moments should equal 0. So we have FBC minus 900, counterclockwise, yeah, equals 0. So from this equation, we can solve for FBC. And then FBC B, so now moment about B. Taking counterclockwise is positive again. So put the right there. And I get 600 times 3. is 0? One of your support reactions might be 0. So then AY ends up to be 0. And then sum of the forces in the x direction, that should give us 0. And that just gives us AX. Newtons. All right. Okay, so let's see. So I'm going to put all these forces up top. So what's next? Cut it, right? At what point? Or are you sure any point? Well, let's read. Getting that. So if I decide to look at the left side, this is my point D. I have AY is 0, so I don't have a free body diagram. And then I have my shear. Since I cut it. So this whole distance is 1 meter. So then for shear, negative 600 newtons. Some of the forces in the x, we have the normal force going to the right, and AX going to the right as well. So then our normal force should be just our equations. Then moment about D. So what does this give me for my moment? Yeah, seems about right. Negative 300. And we have it counterclock, not this one. We have it counterclockwise over here. So yeah, so once we get a negative over here, that just tells us, oh, it's clockwise. Uh, it depends. Diagram as big as possible that you can reasonably. That way you have a lot of room to work with. It's easy to see your values and everything, and all your forces and moments. Hello, hello. Okay. All right. Was to draw our diagrams. So we have a pin support at A. So we have our AY, our AX. So then that just has one force. It can't move in the Y direction. So there's our distributed load. And we could split this up into a rectangle and a triangle. That way we're working with common geometric shapes. And then the center of where this force is going to act is going to be 1/3 from the base. So it's going to act over here, which 1/3 away from here is 1 meter, and coming from the left, it's acting 2 meters away. Newtons. That will be 3 to 5 meters away. For a triangle? Okay. So we have to solve for our forces here. So we could just take moment about where. It could work. Forces don't produce anything because they're in the line. So force in the Y can work. So what direction do you want to denote positive? For moments or for forces? Well, okay, moments you could do counterclockwise. How about for the force, what do you want to do? Or how are you doing it in your calculation? Up is positive? Okay. Minus 300 times 4 plus By equals 0. said sum of the moments, right? Right. I did forces. I was thinking. So we have By. Yeah, we have those forces. Can you tell I'm nervous? I'm kidding. All right. Okay. But anyway, some of the negative 450 times 2. Sine. Yeah, it's just the sign of the moment, right? Because we're going positive. So this force creates what kind of motion? Negative. Then this creates negative. This creates positive. By is equal to what? Three times By. Okay. Yeah, because for our shear diagram, we need the yeah, yeah, it is 650. And then right, this B will produce a jump in our graph, a discontinuity. So you can't really cut it exactly there. That's why we have to get different equations for it. Right. You could do that. You can do that. But also, you don't have the on the base. You have the height of it as well. By inspection, the only horizontal force. So we have to find the height of this triangle. That way we can do our calculations. So by using similar triangles, we can find out this height. So if I get my height for this triangle to be 300 over 3, 100x. Does that make sense? Right, right. Some classes teach it differently, I believe. Yeah. Yeah, because you can use, because this triangle has the same angle over here as this triangle, so they are similar. And because of that, that's why we can apply their ratios and we can equate them to each other. Because we know this height's going to change to our, so now from there, we can get shear and moment equations. Forces in the y will give us negative minus 1/2 100 x squared plus now, have you learned about the relationship between moment and shear? We have a maximum moment, right? So that tells us that we can integrate the shear to find the equation. Right. So well, that depends on the professor. But I figure as long as you know that that relationship holds true, you should be able to do that. But check with your professor one day. Yeah. Okay. But just in case, let's just find our moment. So let's take moment to be positive in the counterclockwise. Yeah, it's just moment. So we have our moment. Keep writing AY, we know that. And then that's 1/6, right? Yep, 1/6 x 100. And you can compare these two, and that checks out. If I integrated then we have to divide well, which 2 times 3 gives us 6. So that checks out. Okay. So you have these values, right? AY and BY? Okay, so I'll erase those. So I'll label this 650. This shear is in newtons. 0. negative 650. They got negative 650 over here. That could have been it. It probably should have been negative there, I'm thinking. That's interesting. No, we did the math right. Huh. My solutions are weird. All right. Anyway, let's start with negative 650. There might have been some error that we had. It says everything should be negative. Okay. Negative, negative, positive. Yeah. Check your math again for when you did when you mind checking your math again when we did the calculations up here for our first diagram? Hmm.
The other day. And then it just goes to weird, actually.
Oh, really? So then bowl.
I don't know. It doesn't explain. But
Because they say this is negative, right?
yeah, which is arbitrary. No. Yeah, that's what it is. So when we take the moment about B, it should be a negative. But we don't take a moment about B, do we? Took a moment about A.
We took moment about A to find B.
Yeah. Take a moment about B to find A.
We'll try it. Let's do it. Let's take moment about B. Yeah. Right? Yeah, so this is negative. Well, yeah, well, are you talking about on the shear diagram or the well, it's just 100. Well, it's 100 divided by 2, which is just 50x squared. Right. Yeah. If there's you get?
Some moments about B, you get a negative impact because it's a rotation.
Okay. Is that what you got too, Joe? Well, for AY. So then this 650 should be negative as far as I erased it. Okay, so good. So now we're back on the right track. So it should be negative 650. So that's probably just error in calculation. Okay. All right, now that we got that square. Okay, so this is our starting point. So next thing we want to do for our shear diagram, we want to find out where our endpoint is. So we want to take this shear region and plug in 3 into our x. Which if we do that, our ending point should be negative. Does that make sense? Okay. And they have the circle. No, I don't use that. Yeah. But if that helps you to use it, then by all means, go. And our moments. Starts at 0. Okay. And then when we plug 3 into the equation, we get the moment at 3 meters to be equal to negative 2400. And x times x squared gives us x cubed. So this is a cubic function. Right. Right. Yep. Because I never learned in that. Mm. Well, I mean, one way you could do it also is just instead of plotting both the beginning and end points, just also do a couple points in between. That helps you see the curve better. The curve of it? Yeah, right, right. Yeah, like I was saying before, just have a table, yeah. Do 0, do 1, do 2, do 3. That'll help to see the behavior of the curve. Yeah. All right, so we've got our first cut. So next cut, we want to do something along here. So I'm going to take the right side of this cut, because left side we'll have a lot to deal with. We'll have the triangle, the rectangle. We'll have a lot of forces there. So it'll be easier to take just the right side of it, because we don't have too much. It could be any arbitrary point. Because when we cut, we're not having force. We're cutting it with the distribution. distance would actually be 7 minus x. And then because this is a distributed loading, we'll have a force in the center. Then if I take some of the forces in the y equals 0, we get v minus 300, 7 minus x equals 0. Which when we simplify that, it's equal to v then we can take our moment. So moment, counterclockwise moment. And we ultimately get moment equals negative 150, 7 minus x. And I believe there's a bit of math involved before we get to this final result. And do the integral, right? Yeah, I'm just going this way just to kind of do the old way, but right. Do the integral, and this becomes 20. You could do the integral and do that too. Okay, so you want, so you.
No, you just get like that. Before when we had it, we left the hypothetical or something like that. Throws me off.
Gotcha. I'll make sure to just like simplify it a bit more. Yeah. No, it's as long as you're learning. We're not plugging 7 because this is 7 minus x. This is valid for, yeah, this is valid for x is greater than 3 and less than 7. So yeah, plugging 7 back in here. It should give us, the two terms should cancel out to 0. You want to check that real fast. And it'll give us that kind of a curve. 300 times 7 is 2100. And these terms will cancel out. So since this is linear, it's just straight line up to 7, or up to the 0 mark. Okay. So aside from that, if you take the integral, it's going to bring it up by 1 order. Talking about factoring out x? Or just in, oh. Yeah, we're good. Diagram. $10.50? Showed it. Oh well, I just integrated the shear directly from the moment. They're just two different forms. Right. the cam is subjected to a couple moment of 5 Newton meters. So we have to determine the minimum force P that should be applied to hold the cam in position. So then this is a maximum static frictional force problem. So drawing the free body diagram is right in the middle. Oh, 10 millimeters. Let me write that clear. 10 millimeters. So 10 millimeters away from this point, a normal force and a static frictional force there. So we have our normal force. And then the cam wants to move, according to that moment, it seems like the cam wants to move in this kind of direction, rotating counterclockwise. So friction wants to oppose that. So we have that. So friction is equal to our mu sub s, or our mu that they give us is 0.4 times NB. So 0.4 NB. Then we have an applied moment. And then if we're isolating the cam from its entire surroundings of two forces there, right? Because this acts like a pin support because the cam's rotating around that support. And we could label that. So I label. O. Because if we do a moment about O, these two cancel out. These two forces creating a moment about O. And that applied moment. So we can easily solve for MB right here, just combining these terms or doing the multiplication out, combining these terms and taking the 5 over. So our NB equals 147.06 newtons. Looking at the cam and focus on the follower. Follower something like this. We got downward force P right here. If NB is going down on this free body diagram, has to go up on this one. What's up? Oh no, you're good, you're good. There you go. Then we do some of the forces in the Y. I have positive going upward. I'll have NB yeah, the friction problems aren't too bad. Just, yeah, it's exactly what I'm doing throughout the whole class. Equations of equilibrium.
And then the frictional, just your normal, I mean, normal forces.
Two normal forces. there's another problem where there's a ladder resting, similar to this one, and it's resting against a smooth wall. It should cancel out at the end.
7 minus x half times 7 minus x times 300 for the moment equation.
Right. Right. Yeah, and then minus your moment if you're taking counterclockwise is positive, gives you 0. It should. Does it not cancel? When we did moments, does that cancel out? It should.
Well, moments don't have to end at 0.
Hmm. Okay. Then I'm probably looking at something wrong. Go back to that one.
Oh, here's where it can cancel out. 7 minus x squared, put in 7 is 0.
Yeah.
Simplify.
It should simplify out like that.
Minus 150.
Yeah, because the other moment, yeah, the final moment equation cancels out. Right, right. It's weird. We'll just come.
Don't worry about it, man. I just wanted to point it out to you.
Yeah, that's weird. I gotta check that solution.
Squared times 150, 2400. It's because you're going down another, or no.
Well, let's not. Because that. But I know Jill's going to use the restroom, so you mind waiting just about maybe 5 minutes? That way, no one gets left. We don't start a new problem right when he comes back.
X squared. It's minus m equals 300.
Yeah, that was the final answer. No, you're right. It doesn't check out, but it should. If we integrate it, it should check out.
Is this Donny?
Right.
Checks out. 7 minus x, 49 minus 14.
They might have something wrong there.
Should be 2100x 150 minus 150x squared, which is what we got.
Yeah.
And then they just did it the other way, and then somehow it works.
Well, let's move forward to the next. See. figures that out. So 50. So we have 2 boxes weighing 150 pounds. So 2 boxes exert 150 pounds, and the coefficient between the boxes is 0.65. Coefficient between the box and the floor is 0.35. So this problem is asking us for the least horizontal force P that we need in order to move the boxes. Okay. These 2 boxes have weight forces. Now we the minimum force P that is exerted on these 2 boxes that will cause motion. So then right now let's assume it's going to tip. So if we assume tipping, our friction force and our normal force, so B. And then since we're talking about like the least horizontal force such that it will move, Fs is at our maximum, which is 0.35, not 6, 0.35, and B. This is 3 feet, which means this distance is 1.5 feet. And F sub S. Yeah, so then we should be able to solve. So let's start with forces in the Y first, since we have 2 forces. Some of the forces or some of the moments?
Take the sum of the forces and the X, so you already have Fs from NB.
Okay. So yeah, so Fs. Yeah, because we got MB. I get what you're saying. So we have Fs. We have NB, so we can get Fs, and that's 105. Move, or we're assuming it's about to move, we can say that it's at our maximum frictional force. And then once we have MB, we can get Fs, and the sum of the forces in the X, that gives us P minus F of S. This is 140, 105. Actually, force, we can only assume that this is the location where it happens.
That's why you have to take a moment about that NB location for Fs, right?
Yeah, that's why we have to do that. Yeah. The 150s come into play when we take moments about here, which is at B. Because we know the entire thing is 3 feet. Weight has to act in the center, in the geometric center of the object. In tipping, our forces have to be located at this point. This 150 pounds is in the center, and this whole thing is 3 feet, we can say that's 1.5 feet. So, well, putting another equation back, the sum of the forces in the x still applies. We still have P minus as for what, the problem or the forces? Yeah. Right. Is that we have to make assumptions about how this thing's going to move. Well, let's not focus on the manual. But we're focusing on the concepts, right? Because if we didn't know what the object was doing, if we didn't know if it was slipping or if it was tipping, then you have to put it someplace around here with some arbitrary distance x. You're right about that. Distance. That's why like that, right? But I know what you're saying. Other problems, you don't know what condition the objects are in. That's why you have to find your distance. That's where that comes into play. But anyway, I'm sidetracking a bit. So, some of the forces in the x direction clockwise is positive. Okay, so moment at B. So these forces don't produce a moment about B. So 150, so I have times 1.5. And is that clockwise or counterclockwise? But it's still, because we're looking for perpendicular distance. Because 1.5 is the perpendicular 150. We could just move this 150 along its line of action. It'll still be the same. And then this force P. What direction does P want to rotate this object about? Negative. So clockwise, right? It's clockwise. Good, good. So those are our 3 equations. So I believe P comes out to be 90 in this case. Do you want to double? So now we want to compare, and this is pounds. So now we want to compare this F sub s to our F max. So F max is 105. Calculated that before. In terms of how this object's going to move. Is it going to slip or not? No, right? Right. Well, let me ask you. If my forces are still here, this object can still tip, right? Box can move alone. So, as long as my forces are there, it can tip. It it's not going to slip because 90 is less than 105. So our minimum force so far right now is 90 that we need to move those boxes. So we need to figure out so we need to draw a free body diagram for top box. Eraser. So now let's assume that this force is 90. Or not assume, but let's carry over the 90-pound force of P. This box moves or not. So we don't need any moments for this one, right? Sum of y, sum of x. S sub s prime and n prime minus 150. No, I got you. Because the coefficient of friction between two boxes is 0.65. And then the normal force in question, which is m prime. 97.5? Well, these boxes will tip. Yeah. Well, I understand that. If we have those forces at the end of B, like if the normal force is right at that edge and the friction force is right at that edge, the boxes are going to tip. However, it takes a lot more force. Does it take a lot more force? Is less than the friction max, then we can safely say that it's not going to slip no matter where. Right. Well, it would tip just because of the fact that the forces are located at the edge. Boxes, they won't slip either. Because we calculated that. Yep. Because even though the force of friction isn't greater than the maximum friction force that you can get, it's because of the fact well, I mean, if it wasn't gonna tip, then our forces wouldn't be located at B. then it'd be somewhere between 150, where the 150.
Now,
Yeah, let's see if I could fit in centroid one and then one moment one, since we have about 30 minutes. I'm going to try to work just through these ones, and then if you have any questions at the end of the problem. All right. Okay. So the top curve, they don't really differentiate it. I'm going to say top curve is y1, and then the bottom curve is y2. So locate the centroid x bar of the area. So the formula for x bar is just the integral of x tilde dA over the integral of dA. So two main values that we have to find. We have to find our x tilde here. So then this will be my x tilde, y tilde. So my base is going to be dx. It's a differential base, small length. Then the area, the height, is just the area. Yeah, 1/2 x minus 1/4 x squared. And then my x tilde is just located some distance away from the origin. So it's just located x distance away from the origin. Dx times our y1 minus y2, and I'll write that all. So we have all of the values that we're looking for. So now just plugging them back in, the integral, and since we're going to differentiate or integrate with respect to x, our limits need to be so from 0 to 2. X squared dx over the integral from 0 to 2 of 1/2 x minus 1/4 x squared dx. Hey, how's it going, man? We're just reviewing, we're doing centroids, and we're going to, it's not too bad. The setup, right. Okay, good stuff, good stuff. But I'll leave you with the final answer. Should be, your x bar should end up to be 1 meter. So if you want later on, you can do the work for this problem and check it out. Are you good?
So
Okay.
now, if you want to keep y, you have to reverse the
Find the x of our equations.
and then you're going to use y.
Well, x. Yeah, don't get just because you're integrating with respect to a certain variable, it doesn't mean that that's going to give you your x bar or your y bar. It all depends on the formula. So if I want to find y bar, all I have to change is that term, the y tilde, y2. But now we need to find my differential element over here. This doesn't confuse anyone if I just like move it over here to clarify the okay. So then the distance from the x-axis up to right. Okay, so everyone's clear on that. I want to my y tilde. I want to find how far away y tilde is from the axis. So I just need to just y1 minus y2. So this centroid is located right in the middle of this rectangle. So this is just half the distance of my h. So then this distance and then I distances and I get my total y tilde. So let me write them over here. So my dA is y1 minus 2 dx. My y tilde is y2 plus so y bar equals the integration from 0 not 0 to 1 from 0 to 2 since we're still working with dx y tilde which would be 1/4 x squared plus, let me use brackets for this, 1/2 of and this is y tilde times 1 minus y2 dx. And 0 to 2 of dA, so just this term, 1/2 x minus. Right. What, you're talking about the midpoint of this? Yeah, the midpoint, yeah, the mid. A horizontal rectangle. You just have to find different equations for it, but yeah, you can do that as well. You could probably do that too. That just means you have to get these equations in terms of x, or well, solve for x. Get them in terms. Y tilde? Yeah, yeah. So y tilde is the center of the differential element. And I need to get from my axis all the way up to the differential element, or to its center. So then the distance, yeah, the distance from here to this first curve is y2. And then the distance from here to here is, I know the distance of rectangle. So we could take 1/2 of this, and since it's a rectangle, it will bring us to that midpoint. Now, if you did, you could also turn these in terms of x if you wanted to say use or but either just depends on how which one you feel more comfortable with.
Put everything as when your y tells me y and your x tells me
Yeah. Moment of inertia. Well, 18 minutes, so we'll go over this moment of inertia. Hopefully I have enough time to do it. Okay. So you're talking about this one. So determine the moment of inertia of the beam's cross-sectional area about the y-axis. Okay. So for this problem, we need to use parallel axis theorem. The moment of inertia of that segment about its centroidal axis plus the area of that element times the distance squared between the two axes. That'll become a bit more evident after the problem. Well, let's see how many segments. All right. So if we want to find, no, I didn't. It's a lot of these composite problems are a lot of the same. You either have a composite body problem or a non-uniform problem, like the one before it. But let's just work through one of these at a time. Of course, each individual segment. So we could say there's about 4 segments, the 2 rectangles up top, the horizontal rectangle, and the vertical rectangle on bottom. So let's do the rectangle. Book in the back of your statics book, they have a list of common geometric shapes and their formulas. It should be all the way in the back. Yeah, it's one of the very last ones, and it has related to the shapes.
I'm allowed to put this in my cursor, but I guess if you're not, my friend said
Some professors don't let you take in material to the test, or they give you the formulas.
yeah, they give you the formula if you need it.
Okay, that to make sure, because I was SIing as well, and
Okay.
professor did that. All right. So let's see. Y-axis. So the moment of inertia about the y-axis for a rectangle, I believe it's 1 over 12 h b cubed. Someone confirm that? Moment about the y? Okay. Yeah, you need to understand this equation. Yeah.
So inertia plus the inertia of x or y plus a dx or dy.
Yeah, it's the moment of inertia of the segment is equal to the moment of inertia of that segment. The centroidal axis of the segment and the axis that you're taking the moment about. So it's a bit confusing. Let's say if I have, let me take the top left rectangle. I'm measuring the moment of inertia of this rectangle from this axis right here. So the centroidal axis of this rectangle, they give those formulas to you. They're in the back of the book on that same page. Plus the area of this segment times the distance the centroidal axis and the axis that you're measuring the moment of inertia about. About y for segment 1, which, let's say, 1, 2, 3, 4 for segment 1 is equal to cubed plus the area of the horizontal rectangle. Is it 100? Plus the area of that rectangle, which is 325 times 25, and then the distance squared. So about the centroidal axis, so the distance between the centroidal axis and the y-axis is 0. There is no distance between them. That y-axis passes right through the centroid of the rectangle. So this is 0, which makes this whole term go to 0. Oh, because the distance is in the center of the y, yeah. Because the y-axis passes through the, yeah. Basically, the y-axis is the centroidal axis. Yeah. Does that make sense as well?
This is for a formula if you're not doing the sum of x's or the sum.
Yeah, yeah. The 112 hb cubed comes from moment of the y about the rectangle.
On the bottom right.
Yeah. It's also taught in physics 1. Yeah. Okay. So let's say I want to find the moment of inertia about segment. So then I have, let's see, that's so 100 millimeters times 25 millimeters for my base cubed plus the area of that rectangle. So segment 3's area is 100 millimeters. The y-axis. So the centroidal axis for 3 is right here. Yeah, 87.5 distance away. 87.5 millimeters. That's the distance between those two axes squared. To find the sum for these, because we still It's like,
175.
yeah, the the one, where did the, which value? Oh, yeah, yeah. Oh, because it's 75 plus the distance to get to the center of the rectangle. The general formula to find the moment of inertia for a segment is this. So to find the moment of inertia about the whole segment, what do you think? What do you think we need to do? Yeah,
What about
sum them all together. Negative moment of inertia.
yeah?
Well, if you're taking the moment of inertia of shape that's not there, that would be a negative. Good, understood them. Okay, cool, cool. So just take some time, fill out that evaluation. I'll give you one right now.
Gotta make a crib sheet of centroid problems.
Yeah. Does filler let you?
Bring in a crib sheet and this.
And as long as you understand them,